It said, every time, like, at least. The course calendar said hardware. Frankly, I didn't feel like it, so I switched the topics around to talk about image processing instead. And we'll talk about hardware on Tuesday. I keep procrastinating on that because I just really don't like that topic. But in any event, I think actually logically in this class this makes a little bit of sense because we talked about color, and image processing is basically sort of like a post-processing sort of thing that happens in a lot of graphics pipelines. Oftentimes we call this image space or screen space techniques, right? Because they're just unaware of all the cool 3D rendering that you did, and now you're just going to go back over all the pixels and edit the image in different ways. And it's worth being aware of these kinds of things. If you like these topics, Fredo Duran teaches an entire course here at MIT on computational photography, which covers a lot of kind of similar topics. But in this class, since every lecture is like a completely different thing from the last one, we get one lecture on this thing. Before we get started, let's see here. So hopefully all of you guys have turned in your homework 5. If you haven't, that's okay, because this is your last opportunity to lose and use your late days. So remember that you're allotted some number of 24-hour periods of late days, and you cannot 3 apparently. Cool. Right, so you can't use them for the course projects. You might as well use them now. My goal is still to send you project proposal feedback any day now. I'm sorry, I'm really busy, but I'm trying. Right, in terms of other announcements, we have your graded exams in the back. Would we be in favor or not in favor of handing them out at the end of class today? Thumbs up. Okay, but I expect no attitude out of you people, okay? That's going to be our deal. But if you do have questions, regrades, and so on, you can talk to me or your TAs, and we'll figure it out. But of course, remember that if you do it in the most diplomatic fashion possible, you're much more likely to get a positive and thoughtful response for your instructors than the usual contact that we receive when it comes to these matters. Any questions about procedural kind of course things? Yeah. No, we're not. Yeah, we're not normalizing. So if you look at the original syllabus for the course, the way that this class is graded, the homeworks and the exam and so on, the sheet tells you like what percentage of your grade each of those is. So we'll just composite all of those numbers together and then come up with one score, and that'll be your letter grade for the course. Will be based on that. Yeah. Any other questions? Fabulous. All right. So today we're going to talk about image processing. This is a very important topic because we can take your photo of your shoe and make it into a cute Instagram photo of your shoe, which of course is a very popular thing and something that happens on your phone all the time. In fact, even if you take a photo on your phone and you don't think you are doing image processing, you probably are. That is to say that just by default these days, when you take any kind of a digital photograph, the kind of amazing thing that's evolved is that the photography pipeline has changed from basically a physical thing, like a piece of film that's absorbing photons, to like this cute partnership between machine and physical world that's mediated very carefully. This is really one of the big developments in the photography world in the last 10, 20 years, which is pretty amazing, right? That essentially there's this nice co-evolution of photography equipment and computational techniques that's happened, that essentially as computers got more powerful, we could do more complicated things to images. And similarly, as our capture technology got better, we could capture more interesting things. And one of the kind of cool things is that we might as well engineer our cameras to work well with computers and vice versa, right? Like, it might be that we don't have to capture certain details because a computer can fill them in very well. And so we should focus our effort in developing our camera some other way. And so this is this discipline called computational photography, which is a big branch of computer graphics, especially at the research level. And really has had a pretty broad impact, right? So these days your phone has like at least like 16 cameras across the back of your phone. Essentially, when you take a photograph with this thing, it merges all these signals together into one really sharp, beautifully contrasted whatever image, which is not actually like a photograph in the conventional sense. Like, it's not something you could have captured with a piece of film, right? But rather is some fictional universe where we've glued together a bunch of images captured using different devices and maybe even at different points in time into just one kind of composite image that to our eye looks better, right? And so this is this really incredible pipeline, which is probably sitting in almost everybody's pocket as we speak today. Right, so these are sort of techniques that now we call computational photography. Back in the day we called image processing. It's not clear to me what the distinction is. But the basic point here is that the computations we'll do today, which are in some sense much easier than what we've done in previous lectures, will all happen on the image grid. Like, we're not going to worry about the fact that our scene contains 3D content, but rather we're just going to iterate over pixels and do sort of post-processing. And this is something that happens everywhere. It happens in your camera. When you're, if you work in a film studio, you'll spend a lot of time it's very difficult to film the Incredible Hulk, so I'm going to like put him on top of like a filmed scene between the other characters, which are actually humans, and it's exactly the same technology going on there, right? And so it's worth spending at least one kind of lecture. So the nice thing about today's lecture is that we're back to 2D. We're basically going to disregard 3D content, although this isn't 100% true. I mean, there are plenty of image processing techniques that at least try to kind of weakly understand what's going on in a scene before you do your image processing, because obviously 3D cues matter a lot when you process an image. So a good example of that is like, maybe I want to simulate having depth of field in my photograph, right? So I think the new iPhones have this feature, right, where you can kind of pretend like the background of your scene should be blurry and the foreground shouldn't be. That is an optical effect, right? That comes from having different shaped lenses. But like your iPhone camera clearly doesn't have that. It's like a little flat doodad. And so what's going on is this computational pipeline where in that case you have two photos, or I guess three now, based on taking pictures with multiple cameras, which gives you some weak notion of depth, and you're using that to simulate a 3D effect, which in reality is much more complicated. That's a great example where really you're leveraging the fact that your perceptual system is this kind of blunt object that like doesn't understand the finer grains of some of these depth cues, right? Like when you look at the blurred out scene, like the background's blurry, so you're happy, even though maybe it isn't actually a lens effect, right? And so that's a nice kind of partnership between algorithms and hardware, which is sort of what we'll be talking a lot about today. So when you read literature in this kind of area, depending on who you talk to, it might be written in two different fashions. You guys are all advanced computer science students, so if you were to represent an image, you'd probably think of it like a 2D array of numbers. We've already done that in this class many times. But the one thing to notice is, of course, a different way to think about an image is more like a function, right? So at every point x comma y in the plane, maybe I assign that point a color. Obviously, in reality, that's not what's going on in image processing. But essentially because of that, depending on what textbook you read, sometimes you'll see like discrete stuff like sums, sometimes you'll see continuous stuff like integrals, and the important thing is just to know that like when you kind of squint at this literature, it's not going to matter, right? Your computation is going to happen on a grid at the end of the day anyway. So this is largely just a modeling decision. Of course, in addition to image processing, one thing we often do is process video. So what do we do? Well, if images are 2D arrays of numbers, then videos are kind of like 3D arrays of numbers, right, with one frame per index. And this is actually a perfectly reasonable thing, right? Like I can blur out my video in space and time, or do interesting effects that try to edit the content of a video. I would say that image processing is an extremely advanced discipline, and one that we have really powerful tools, right? Like when you download Photoshop, there's like a ridiculous number of neat things you can do. Video processing is far behind that discipline, although it's catching up, right? So if you download, I don't know, what's the video analog of Photoshop? It's Premiere, right? The tools there, they tend to be inefficient, a little bit slow to work with, and there's a big issue, which is temporal coherency, which is namely oftentimes you'll have these cool image filters that do really advanced stuff. They like round your pixels and do these discrete decisions and try to like make your image look painted or whatever. But then what's going to happen if I apply my filter just to every frame of a video sequence? It might be that there's like some randomized component or some noise that I introduce that like is okay on one frame. But then when I play a bunch of frames in sequence, it just looks like a mess. And that's a very common scenario to be in. So for example, these days a very popular thing to do, at one point we might have called non-photorealistic rendering, right? So that would be like taking a photograph and then coming up with some filter that makes my photograph look painted, right? So like these days you would use a GAN or whatever machine your favorite style transfer learning thing is. These things are typically trained on images, and one thing you'll notice is when you play if I just took all the frames of a video and put them into this filter one at a time and then played them all back, it looks pretty terrible. because suddenly you start seeing all the artifacts that you might not have noticed in a still image. So anyway, this is this idea of temporal coherency. And in some sense, it's a made-up problem, right? Like if I have an image filter that is trying to make an image look like a painting, like paintings don't move. So it's like not totally clear what the objective function should be for a problem like that, which is part of the issue. But in any event, okay, so we know the images are sort of 2 or 3D arrays of values. Specifically, what are they? Well, you know, maybe disregarding a little bit our discussion of color, I think a pretty typical abstraction is to think of an image as just a big 2D array of red, green, and blue values. And image processing essentially inputs one of these things and outputs another. Yeah, simple enough. Okay. So let's come up with just a simple example of this. So for example, if I wanted to brighten an image, I could take these numbers and multiply them by a number bigger than 1. If I wanted to darken it, do the opposite of that. A slightly more advanced one is compositing. So here we have a video. I tried to find the most poorly composited video I could find on YouTube, and this music video did the trick. But in any event, in compositing, you have like a singer in front of like a green background, you know, and then what do? You like put them in an interesting scene, and so you composite their image on top of, you know, just some photograph that you might have. If you ever want to detect a composited image, a good way to do that is to look, so for example, if we look at Rebecca's shoulder here, what do we notice?
White outline.
Yeah, we notice a white outline. What's going on here? Yeah.
It's really hard to determine the exact outline in whatever your foreground is supposed to be instead of trying to extract it.
But even if I did, like let's say that I cut out her shoulder exactly perfectly. I know exactly what pixels are inside and outside. What else goes wrong? So she's singing in front of a green screen. Is the environment that she's in green? No, but what am I seeing on her shoulder? Yeah.
The light, because
Yeah, I'm seeing green light reflected off of her shoulder, but physically that doesn't make any sense given the background that I just replaced it with. Right? So if you're ever trying to detect a composited image, that's the best way to do that. Now the reason that we're leading with this example, so this is called compositing, or it's kind of like combining visual elements from different sources. And in the graphics pipeline, this is a huge thing we do all the frickin' time. Not just in photography, but also, for example, in the movie studio pipeline, like maybe an actor's time is really expensive, so I'm going to just film all of the scenes with that actor in one afternoon talking to, like, you know, some stand-in for the other character and then composite them together later or something like that. And the question is RGB enough for that? The answer is probably not, because what information am I missing? I'm missing what pixels do I actually want to use, right? You know, in the green screen, essentially the green color is telling me that I do not want those pixels in the image, right? I would like to remove them and replace them with the background. And so typically in applications like compositing and in most major image file formats, in addition to having RG and B, we have a fourth channel. This is A. A stands for alpha. And this channel is kind of like transparency. Okay? So the way to think about this is that it's kind of like the fraction of a pixel that is covered by that pixel's color. If you think about it, this doesn't make any sense, right? I mean, like, either you're there or you're not in a pixel, but this is going to be a way to kind of take a weighted average between images by using these alpha values as the weights in the weighted average. Does that make sense? Cool. All right, so this is a technique known as alpha blending. So probably what would I do? I would film this person in front of a green screen. I would look at every pixel color and measure its distance to the green color that I know shouldn't be there, right? And essentially cook up an alpha function, which is a function of that distance, right? Like, so if it's very close to being green, I probably have alpha equals 1, meaning like this pixel just shouldn't be there, right? Or alpha equals 0, depending on your, actually alpha equals 0 I think is the standard, meaning 0 would mean that you shouldn't use the pixel color, 1 meaning it should be there completely. Okay? So compositing is our very first example of a simple image filter. Looks something like this. So let's say I have two images, a foreground and a background, and moreover the foreground image has an alpha channel. Then what I could do is loop over every pixel, and if I want to compute the color of the composited image, I'll take alpha times the foreground, 1 minus alpha times the background, and add them all together, right? So this is like a weighted average of the background image and the foreground image, where alpha is the weight. So yeah, so alpha equals 1 here is saying opaque, right? Meaning the foreground should be on top. When alpha equals 0, then the background is on top. This is already our first kind of baby example of something that could go wrong. Oftentimes, image file formats do not store RGBA, but rather they store something called premultiplied alpha, which is, let's say I know that I'm going to composite this image. I'm never going to use it by itself. This is the case for like icons, right? So oftentimes I'll have like an icon on my computer, and I know that I'm always going to like stick it on top of a window. Well, there's like never a case when I'm going to need C sub f. Right? Every time I see C sub f, the first thing I'm going to do is multiply it by alpha, right? So in that case, one way that you can save yourself a multiply is to say, okay, my image file format doesn't store color, it stores color scaled by alpha. And the reason for that is it saves me one little piece of arithmetic per pixel when I composite stuff together. Does that make sense? Yeah. So when you read off numbers in an image file format, you've got to be a little bit careful. So here's what this compositing process looks like. So we have this very 80s guy in a leather jacket. And of course, we can choose different background colors. And why do we use the color green? You've already chatted here. Wait, this is an easy one. Yeah.
Usually people aren't green.
Exactly right. Usually people aren't green, right? And so you want a color that's far away from what you actually expect to see in the foreground, because otherwise, what's going to happen? They're going to disappear. Yeah, they'll do that. Exactly. Yeah, so you want a color that's far away, probably from skin color or anything else that you expect to see. I think green is a pretty safe bet in that regard. And otherwise, what can happen are things like this news clip here. Let's see if it'll play.
Well, you got a tell about your wardrobe malfunction at the wedding, Kim Kardashian's wedding, and then you had one a short time ago. Here, this is real. The green shirt you're wearing, and it just...
Right.
Yeah. Season 101, my friend. You can't wear green.
Yeah, so if you watch... So if you watch the news in the morning, you'll probably notice that there's at least one color out there that all of the newscasters are not wearing, and that's probably the color of the screen that's behind them. Yeah, sometimes it's green, sometimes it's blue. It depends on, I don't know, I guess their preferred outfit. Right. So anyway, this is a kind of an old piece of technology. There are a lot of problems with it. I mean, one of them it actually limits the clothing you can wear, which isn't great artistically. And the other is that the screen itself reflects certain color of light off of the subjects in front of it, which can create some of these unnatural effects right at the boundary. Does that make sense? Okay. So actually, there's kind of one kind of fun thing about alpha channels that's worth knowing. Remember that when we talked about ray tracing, we talked about Boolean algebra and how you can use it to to construct new shapes. Like we had the intersection of two shapes and like the union of two shapes, the exclusive or whatever, so the difference. You can use alpha to do the same thing, right? So let's say that I have an alpha channel for both the square and for the circle, right? And the alpha is 1 when I'm inside, 0 when I'm outside. Well, then there's an entire compositing algebra, which is essentially just a way to get all kinds of different effects, right? Whether it's, to put one thing on top of another, to subtract one thing, and so on. So for example, let's say that I wanted to find all the pixels in the blue square that are not in the orange circle here. How could I do it? I think this is the easiest one. So what do I want? I want them to be in the blue square, so the alpha in the blue image has to equal what? 1, right? What should the alpha in the orange equal? Right, so the alpha channel I want in the composited image should be 1 when this guy is 1 and this guy is 0 and 0 otherwise. How could I get that from the two alpha functions that I have here? Yeah. Multiply the alpha values, right? Yeah. Is that right? Actually, wait, I'm sorry. No, that would be the intersection, right? Oh. Yeah. Sorry, I was too agreeable.
It's like the square is 1 and the circle is 0, so you take the, like if you multiply 1 by 0, you get 0.
No, that's not quite right. So the alpha channel of the circle image is 1 inside of the circle.
Is that for the one?
So it's true for all of these. So the input data is 2 images, one of a square and one of a circle. Or the alpha channel is telling you which one's which. Yeah, so we're almost there, but I was a little too agreeable. Yeah?
You can subtract and then clamp to 0 and 1.
Yeah, there are a lot of different ways you could do it. So let's say, so in particular, let's say I have a circle image, we have a square, and I'm going to look at the alpha of each of these and then say what should be the out. Right, so we have a few cases here. So if this is 0 and this is 0, then what should my out alpha be? Also 0. Okay, so remember that I'm looking at this one here, right? Okay, so let's say that I'm in the circle and I'm out of the square. It'll be 0 again, right? Let's say that I'm out of the circle and in the square. 1. In the circle and in the square. 0, right? Because I'm trying to subtract the 2. Yeah, so I want a function that takes in alpha circle, alpha square, and gives me back these numbers for the binary things. Can any of us think of one? Yeah.
You can say like square and not circle.
Square and not circle. Okay. Let's see if I can write it in, what is it, conjunctive normal form. How do I write this in terms of algebra? Like these are numbers, like 0 or 1. So I would have alpha square multiplied by 1 minus alpha circle, right? So if I use that, then I'll get this, this out effect over there. So anyway, that's the sort of thing that you can do in compositing algebra, is work through basically for each of these circumstances, like this guy should be on top, that guy should be on top, whatever. You can like work out your little table here to figure out the right formula in terms of the alphas. You can always write it algebraically as like a product. And then, yeah, what comes out is a whole host of different ways to combine images, which is pretty neat. Yeah, and so if you look even at like pre-computer graphics software, like hardware implementations of green screens and so on, they would basically give you these sorts of options where, in that case, it was just hardwired into the circuitry rather than done computationally. I think these days, of course, this formula is just carried out on your graphics card. By the way, this is like made for shaders. Do you see that? Because this is just like a formula going to apply to every single pixel. Every pixel moves independently of every other pixel. This is a really great example of something that'll work well on your GPU. Cool. All right, so this is just one example of sort of a color space style operation where generically there's many different things that I might want to do to an image that just involve looking at every pixel, taking in their colors, and then doing something to the color of the pixel and outputting it, right? And this is a great example of a SIMD process, which is something we'll return to on Tuesday. Anybody remember what that's called? Yeah. Single instruction, multiple data, right? The idea that like I've got a ton of pixels, and every single pixel I'm going to put through the same function f, and they're all going to do it independently of one another, right? So like if you guys were to write like threaded for loop code, this would be super easy to parallelize, right? And so that's what graphics people really want to do, right? They don't want like the color of this pixel to depend on the color of that one, because then our multi-threading becomes much, much more complicated. Cool. So there are many color space operations out there, of which compositing is just one. Let's go over a few other ones. So maybe I want to adjust the brightness, then roughly I could just take my image and multiply it by a constant, right? So as the constant gets bigger, the image gets brighter. What can go wrong? Yeah.
Or if you get a value over 1 or 255.
Yeah, so let's, for today, we'll assume our image values are between 0 and 1. That doesn't make a big difference. Yeah, if I multiply by a number bigger than 1, and I already had a white pixel, I'll get a more white pixel, which is a little unclear what that is. So in practice, what ends up happening there is it just gets clamped. And so if you play with your phone and you like push the brightness controls to the extreme, what you'll end up seeing are like bad sharp edges, which is essentially where the color reached the top level and then just leveled off, right? So you can't see any interesting content inside of that part of the image. Here's a more interesting one, which is increasing the contrast of your image. Can you guys see the difference between the left and right image here? What's going on? Like, what's going on in a contrast filter? So there's a very typical way to visualize what's the sort of contents of an image from a color perspective. So let's just think about the brightness content. So we're going to disregard RGB and just think like black to white, okay? So let's make a plot. And here we're going to have brightness. And over here, I'm just going to have, the number of pixels. Like I could collect a histogram of these values. So in the left image, right, the left image is pretty boring. It's kind of grayish. What does this histogram look like?
Bell curve.
But a bell curve, but specifically, what's the property of the bell curve that's making this image look kind of grayish? We've already called you. Here you go. What was that? Yeah, its deviation is lower. A different way to put it is it's just like kind of occupying a very small piece. Like maybe there's black and there's white, right? So all the colors are in some small range. So what should I do in that case? How can I fix this problem? I'm guessing you have an answer. Yeah. All right.
I mean, you have some minimum and some maximum that you're normalizing.
Yeah.
A bigger range.
That's absolutely right. So for instance, maybe this image really literally only has colors that are between here and here. There are just no colors that are darker than, some number and lighter than this other one. Right? So then one thing I could do would be to rescale the colors in the image so that this color is exactly 0 and that color is exactly 1, right? And then I'll get a histogram that looks kind of like that, right? So in other words, I'm using up more of the sort of, like you can think of this horizontal axis as all the colors that my screen knows how to display. And somehow what I'm doing when I adjust the contrast is trying to use maybe a bigger portion of that gamut. So in general, many of you have probably seen these, these visualizations, right? You can think of, you have some histogram here, which is your original color content, and then when you run it through some function, so in this case, right, this function is just saying clamp everything and then move linearly between the min and the max, so that's just like stretching stuff out, right? Then you can think of this as like just a function of all the pixel values, that's inputting pixel values and outputting new ones that maybe use more of your range, right? And of course, in some contrast filters, maybe you even take this line and you like squeeze it in a little bit, right? So that you're like, maybe there are just a few pixels that I'm willing to clamp at 0 or 1 in exchange for getting better contrast in my image. By the way, that's roughly just what's hardwired into, like, if you have a computer monitor, there's that little contrast button on there, and I believe that's roughly what's going on there. It's just scaling. Yeah?
Do you have to account for, like, the perceptual differences between like, blue and red and green?
You should. Yeah.
Is that just affected by the fact that you're multiplying and
Yeah, so this is a great question. So the question was like, well, perceptually we perceive red, green, and blue a little differently. Should we account for that? The answer is absolutely. So a very common thing to do would be to take your image. You can put all these operations together. Like I could take my image, convert it to a color scheme that tries to separate out brightness from color, then apply this filter on that channel, and then convert it back. And that's a very, very typical thing to do. That's absolutely right. And this will become even worse when we do nonlinear image filtering, that like, if you do the same filter on red, green, and blue independently, you might actually, for example, have sharp edges that end up slightly misaligned in those three, which can be kind of a problematic artifact. Right, so yeah, so maybe we'll return to that a little bit too. When we talk about tone mapping, you'll see that's another good example of using perceptual issues. Of course, we can also desaturate our images. So in this case, maybe what you do is take red, green, and blue and move them closer to the average of red, green, and blue. Right, because the gray value is roughly just the average, like R plus G plus B divided by 3. Right, so I can maybe take the color channels and move them closer to that per pixel. One small thing to return to your question here, again, we are more sensitive to red and green light than we are to blue. So maybe when we convert our image to grayscale, we actually don't just weight those three evenly, but rather we use some weighted average. So like the weights in this weighted average are roughly the ratio of the different cones that we saw in our previous lecture. So it's a very common technique. So generically speaking, what is this visualization doing? It's inputting a histogram and then running your pixel colors through some function and then outputting another one. A very common tool that you'll see in image processing software like Photoshop is to just give you control over that function. So that's, how many of you guys have seen a user interface like this before? Yeah, quite a few. So essentially what's going on here is it shows you the distribution of colors in your image, or maybe distribution of brightnesses or whatever. And then rather than just like giving you one knob to turn, it literally says you can just draw whatever function you want that remaps the colors. Right? Like maybe I want my photograph to be black and white, in which case what do? I like clamp, I just have 0 and then 1 here, and that'll take that histogram and just stick it on the two ends. Or I could do something really crazy, like maybe I take the middle brightnesses and map those to white and then like map it back down, like for some reason that's all I care about. But rather than just giving you some predefined versions of this function, the high power tools just give you control. You can draw whatever you want. What do you think is driving these user interfaces? Like how are they actually drawing that function? Yeah. It's a Bezier curve. That's absolutely right. So what are you doing? You're asking your artist to draw a spline curve, and then you just run that every pixel in your image through that spline curve the artist drew. So yet again, it's the same technology that comes back. Okay, so those are our sort of really simple linear style image filters. They're not linear, I guess, but just per pixel. And there are many other ones too. So here's another example of a really problematic image. So when you look at the typical research papers in computational photography, you'll see a lot of photos of churches. I don't think it's because graphics researchers are particularly religious, but rather these are great example of a particular issue that comes up in computational photography all the darn time, which is known as dynamic range. So in particular, what's so weird about the scene here? Is it like what's kind of a distinguishing property relative to like a happy, bright, sunny day? Yeah. That's right. So when you're in like a cathedral or whatever, a very typical scenario is that these are big buildings made of stone, and then right in the front of the building is this giant bright light, right, for dramatic effect, which has exactly the effect you would want. Some stained glass window, and what's happening scientifically, of course, is that there's like a ton of photons coming in at a very small portion of your image. So what's going to be the problem with this? Photographically, like there's 6 different orders of magnitude of brightness going on in a typical image here, right? Like there's really dark stuff on your left, really bright stuff right in front of you. What happens when I photograph? Well, when I photograph, I have to choose how long the shutter is open, right? So remember how a camera works. Like my extremely bad understanding of how a camera works is you have this sensor, you open up the shutter for a second, probably a lot less than a second. Photons start pouring in. You have the sensor that's receiving the photons, and then the shutter closes. And then roughly, the photograph that gets communicated to your computer is kind of proportional to the number of photons that hit each sensor. But there's a problem with these sensors, which is that they have kind of a limited range in terms of the amount of stuff that they can sense, right? They can overflow very easily and so on. By the way, this is similar with your eyeball. So what ends up happening, well, is an issue that looks something like this. So the stops on your camera is sort of the amount of time your shutter's open. So let's say that I'm photographing a really sunny day, and for some reason I've pointed my camera directly at the sun. By the way, this is not advisable, just from an artistic perspective. But even with an extremely short shutter speed, something interesting is still happening in my image, right? I can see the sun because the sun's really bright. It's sending a lot of photons in. So I open it for this tiny fraction of a second, and it already saturates, right? On the other hand, of course, when it was that quick, well, in the dark parts of my scene, I didn't wait long enough, so maybe no photons came into the sensor, and so I just have noise, right? Like, maybe just like some spare photon kind of wandered its way in, but not enough to get a coherent signal of the world. So what do? I adjust my camera, which, maybe I turn a crank, but I guess these days you hit some button, right, then the shutter speed becomes slower. In other words, the camera opens up for longer. And now what happens? Well, if I adjust it all the way to 0 stops, well, now I'm capturing the dark parts of my scene, right? Like the grassy path here, or the water, or what have you. But what went wrong? Well, yeah.
The sun looks like really big and crispy.
Yeah, the sun looks big and crispy. I have to think about that one. So that's absolutely right. So the more technical term here is blown out, right? That essentially up here, I'm not getting any interesting signal because the sensors for the image in front of my camera saturated. They just said, okay, like there's a lot of photons, like I don't have anything more interesting to say, right? So in the time that my shutter needed to be open, in order to capture enough photons to get a detailed image down here, I've actually blown out the interesting detail around the sun. So this is both a problem in capture and in display, right? Because even if I had somehow beautifully captured this image, or even rendered it for that matter, it turns out when you put it on the screen, if you display the actual colors that came into your sensor, it probably wouldn't look so great. You'd probably just have like one bright spot and then like a lot of boring stuff. And that's because your eye is not sensitive just to color, it's sensitive to ratios. Remember we talked about that last time? And so when you design a photograph, it might be that you don't want to simulate the world around you. You want to kind of simulate a photograph that's really capturing the ratios of different pixel colors. In other words, that you might want to do your computation on log scale. And this is really a problem depending on the type of scene that you're trying to display. So for example, in a sort of sunny landscape, like the example in the previous slide, you can have a dynamic range of brightnesses that's like a range of 100,000 to 1. That makes sense because the sun is really bright. You know, right, but unfortunately, the typical, you know, capture and display devices like your eye, cameras, glossy and matte printer paper don't have nearly this amount of dynamic range that they're capable of. In other words, the ratio between the brightest and darkest color that I can draw on my computer screen is not 100,000 to 1, it's like closer to 1,000 to 1. Does that make sense? So your display is just not capable of the dynamic range that's around you in the real world. And so what do we have to do? Well, we kind of want to simulate the same look, but our display technology is a lot worse, right? In fact, the worst possible example is like printing on a sheet of laser printer paper, right? Then your dynamic range is like 50 to 1, which is like remarkably high, actually. I wouldn't have guessed. So in any event, there are a lot of really clever tricks that people have to get around this. This is our first example where we're going to do something where we basically fictionalize an image that wasn't there. So here's one neat trick. This is called exposure fusion. So here's what we're going to do. This works great in static scenes. Here's another church. We're going to have a lot of churches today. And we're going to set up our camera on a nice tripod, and now we're going to take, instead of just one photograph, I'm going to take 4 photographs at different f-stops. Okay? And so take a look at what this looks like. So over here, I capture that nice stained glass detail, the edges of the windows and so on. And then as I move to the right, okay, well now the windows just look blown out, but I capture like the floor and the chairs and all the internal stuff in the church. And then in exposure fusion, what we say is like, okay, well now we know the actual dynamic range we're trying to capture. We took care of the issue with our capture device, our camera, right, just by using different f-stops. But we still have this secondary issue, which is that our computer screen can't display the scene that we just captured. So what we're going to do is make a new photograph, which is not a real photograph. This is a composite of these 4, where for every pixel, we choose its color from one of these 4 images, or maybe blend them in such a way that always the dynamic range locally is within some prescribed kind of range of values. Right? So in other words, we're going to rescale the brightness depending on other brightnesses that we see nearby. This is a fictional image. Do you see that? Like this is way brighter in the interior of the church and way darker near the windows than actually happens in physical reality, but it's trying to make use of the entire dynamic range of your computer screen to give you some representation of the scene that you want to see. And notice that your brain is perfectly happy to parse this as a real scene, right? It's not saying like, oh my god, this lighting doesn't make any sense. What can go wrong with exposure fusion? Why don't we use this every day? Actually, we do use this every day. Your iPhone camera probably does this by default. Let's say I'm photographing a basketball game.
I mean, like, you're using a whole bunch of
Yeah, you're using a whole bunch of images. Yeah, in particular. That's right. So like in sports photography, this technique is completely useless, right? Because I have to take a bunch of photographs, and in the time between the different photographs I've taken, stuff has moved, right? So when I average these things together, I get like some composite of different motions that are glued together in a creepy way, which is really a big issue in this area. So what do people do? Well, some modern computer vision algorithms can kind of cope with this. Like maybe they actually warp the images a little bit and then do exposure fusion, but that's becoming very expensive, right? Like suddenly you have to do quite a bit of computation to make up for the fact that your camera technology is not so good. Incidentally, there's a kind of an interesting technology that was an extension of this basic idea of exposure fusion. It was proposed simultaneously by two research groups, one of which was at MIT, I forget where the other one was, where they say like, okay, let's say that I want to take a photograph of like a candlelit dinner somewhere in a dark room. And it's a good example of, I can do two things. I can mess with my camera hardware and I can mess with my software in a way that captures that room as best as possible. So in particular now, I'm going to attach a flash to my camera. And now why is the flash there? Well, if I want to photograph, you know, a dark scene, I can open up my shutter and I'm going to get a very noisy image because the shutter has to sit there open for a long time waiting for photons to come in, and they just don't come in all that often, right? So there's a little bit of speckle noise, what we call shot noise. And so one thing you can do is say, okay, well, if I want to take a photo of my candlelit dinner, I can turn on my flash, take a photo. Now I get a perfectly sharp image because I just put light everywhere. What's wrong with that image? Well, if I wanted to capture the romantic candlelit dinner scene that I'd so carefully laid out, I didn't, right? I just like flooded my room with bright white light and then took an image and like, yeah, it's detailed, but it looks like Costco, you know? So how can I fix this problem? Well, there was a clever idea that said, what I'm going to do is rig my camera to very rapidly take two photographs. One, I'm going to take without the flash, and one I'm going to take with the flash, right? And now what do we know? We know that the image with the flash has really interesting sharp edges and like all the detail that I need in my image. The noise level is very low, but the colors are really bad. Now there's a second image I'm going to take where the colors are more or less right? I mean, there was no flash, so I can capture all the sort of look of my scene. But the noise level is very high. So what do? I come up with a computational technique that uses the colors from the noisy image, but the sharp edges from the bright one, and fuses them together into one composite thing that looks like a much higher resolution version of the same scene that sort of composited these things together. So it's a clever trick. This is called flash, no flash photography. And it's one of the sort of technologies that was one of the precursors to a lot of the computational photography we see today. I have a good friend at Stanford who proposed vampire, no vampire photography. Anyway, it was a really clever trick. You know, if you have, you can't see a vampire in a mirror. So he has this technology where you have a beam splitter, and so the light comes in like this, and you have two sensors, right? So like one image goes this way, one goes that way. But this one was reflected, so you can't see the vampire. So when you subtract those two, yeah, never mind. Okay. Right, so even if you do capture dynamic range in a single photograph, that doesn't mean that you'll be able to display it, right? This is a separate issue. There's two issues. One is capture is annoying, like your photograph, you know, if you have too long an f-stop, it gets blown out. If it's too short, it's noisy. The second issue is like, I want to print my photo on a piece of matte printer paper, but my printer doesn't have the kind of, you know, my printer can't like blast out light the same way that the sun does. So to solve that second issue, this is an issue, a technique known as tone mapping. So in tone mapping, what I want to do is take the tones that are present in my digital image and map them to the dynamic range of my display device. And so a very typical thing to do is, you know, maybe just rescale your image to the dynamic range and so on. More advanced tone mapping techniques try to kind of better saturate the full gamut of colors that your display device is capable of showing. So for example, in that brightly lit scene, what's going to happen if I just scale the colors so that like the sun becomes the brightest color my printer knows how to print and the grass is the darkest color? Yeah.
And then you're just going to have like a very, very bright sun and then everything else can be dark.
That's absolutely right. When I linearly just scale my image just to the tonal range that's possible in my display, that's not necessarily such a great idea because I'm just going to end up squashing all the colors to just make up for the brightest color in my scene, right? And so oftentimes you see these photographs. I purposefully chose, don't tell my friends this, like some images that I think look kind of bad, which is this exaggerated effect. You often see it in photographs of the sky where there's like this weirdly dramatic range of colors. And so what's going on here, is sort of a more aggressive tone mapping technique that's trying to use a bigger piece of the range of intensities available in your display device. So the basic issue that these kinds of algorithms try to solve, largely on like bad Instagram channels, is that if I just do linear tone mapping, which is just taking the tones present in an image and scaling them to fit the tones I can display, the image tends to look very flat, right? Because it's just dominated by the bright colors in the image, which maybe occupy a pretty small piece of the content. And so a more typical thing to do is to take the log of your image, rescale that thing, and then put it back through the exponent. The reason being that what your eye is sensitive to, again, is ratios of color, right? And so what matters more when you do that rescaling is not necessarily that like, that the exact relationship between every pair of pixels is preserved, but rather just that the contrast is preserved. And so a nice way to do that is just in log space. And the end effect of this is just brighter, dark regions in an image, right? That's basically it. There are many ways you could have done that, but that's the basic technique here. Right. So I think that basically covers all the image filters you could possibly do per pixel. But of course, there are many image filters that involve more than one pixel at a time, so we should spend a little time talking about that. So we've already seen some examples of that in this course, right? When we talked about mip mapping, what did we do? We took a big image, we shrunk it down smaller and smaller and smaller, but those smaller images in the mip map are basically like weighted averages of pixels in the original image, right? So here's my mom's cat, and I shrunk her down conveniently. PowerPoint lets me do this very easily. And of course, as I do that, all of the nice detail in Samantha the cat here gets preserved as I go down from one scale to another. And of course, this is actually already kind of a tricky image filter, and one that we've talked about a bit in this course, right? Because as you remember when we talked about rasterization, when we make images smaller, we have to account for the fact that a single pixel in that small image can cover a fairly large amount of space in the original one, right? And so basically the same techniques we've already talked about for mip mapping and shrinking images and dealing with aliasing and so on apply here, as do the same issues. Essentially the algorithms here are identical to the ones we've already covered in this course. So for some examples, right, maybe I want to do minification. I want to take Samantha and make her smaller. Then of course there's a bit of a challenge here, which is if I mark 2 points on this smaller image, they become pretty far apart in the larger image, right? And so the typical thing for me to do is to say, well, the pixel color in the shrunk image is kind of like the average pixel color in a neighborhood over here. Yeah? It's pretty amazing, by the way, that your CPU can do this as fast as it does, right? Like when you play with Photoshop, Word, whatever, you're moving images and shrinking them and resizing them, and it's totally transparent to you that behind the scenes is computing an integral, right? This is the tiniest bit magic. Incidentally, what should I use as my kernel, like my weights and my weighted average? Does anybody remember? Remember our Fourier? Began with a B. Box is what I would do in the Fourier domain, and in the not Fourier domain, what would I convolve against?
I was going to say.
What was that? 10 would be an approximation. What was that? Sinc, right? Because remember that sinc is the Fourier transform of box. So it's this weirded weighted average that gives us the optimal reconstruction filter. I'll let you guys revisit that lecture to remember how that works. And of course, this minification thing happens locally in rasterizations too. And it's just an integral against some kernel. Of course, the opposite of minification is magnification. This is probably the easier one to remember how to do on an image, because in some sense, there's only so much information that's there. Right? So when I make an image bigger, I can't really invent image content. Right? So for example, in this course, we talked about bilinear interpolation. Is bilinear interpolation necessarily such a good idea in photography? It's fast, I'll give it that. What does it do? And you guys have undoubtedly experienced this. If I take a photo or zoom in really close, yeah.
It doesn't do edges well?
Exactly. This doesn't capture sharp edges at all, right? It just smooths them out. But if I take a photograph of something with a sharp edge, it's not all that unreasonable that I might be able to like trace that edge, for example. right? And then I could use that information to build in a sharp edge in my larger image. Now from a Fourier perspective, have I done anything? Probably not. Like probably this is equally good or bad to just using some simple interpolant. But from a perceptual perspective, this can make a big difference, right? So some of the modern tools, this is like what a bilinearly enlarged image looks like. So we have this, well, I don't know what this shape is, but when I enlarge a little piece of it, what you can see is this extremely blurry object. But if I look at the original image, it's pretty clear where all the interesting stuff is happening, right? Like there's a certain kind of line that you could trace. And so some of the more modern techniques for image resizing will try to like trace those lines and then incorporate them in the larger image in a way that says like, okay, I don't really know that this content is here. I can't really do this. But perceptually, this looks a heck of a lot better than the blurred out object. Yeah? And so there are a lot of different methods for this. They change every year, and yeah, they're kind of fun to play with. I don't think that these are implemented by default in a lot of your like what word processing kind of PowerPoint style programs. Right? I think they look more like the top row. But this can make a big difference if you really care about enlarging something. By the way, this is extremely close to algorithms that do vectorization. Right? So vectorization would be like, I take a scan of a cartoon and I want to convert it into a bunch of Bezier curves. So the first step might be to detect all the edges and straight lines, and then after that you have to trace them, which is a problem I know and love. So our group works on this quite a bit. And of course, in sampling, we don't just uniformly resize things. We can stretch, rotate, and so on. And in each case, essentially all we're doing is pretty straightforward, right? In the rotated image, I compute its coordinate in the original photograph. Maybe that coordinate isn't precisely at a pixel location, so I have to interpolate a little bit, and then I put that color back on the original guide. And in fact, there's no reason why you have to have the same transformation everywhere. So at one point in my old graphics class, I used to have people implement this moving least squares techniques where every point on the image gets a different transformation matrix that I kind of smoothly interpolate. Right? So this is telling, remember, all I need to do is like be able to look backward in the input image, read its color, and then put it in the processed one. So maybe like I want to take this cat, and now if you look, there's some red points marked here. I can like stretch them out, make his ears bigger. Then what I can do is say like, okay, he wants to translate over here. He wants to translate over there. So I'm going to interpolate some translation matrix in between these two control points and use kind of a local version of those same filters to get a transformed image. This makes use of something called generalized barycentric coordinates, which is a cool technique in graphics. So other things that we want to do with photographs, other than just stretch them out, is blur them out, is another common one. So for example, maybe I take a very sharp photograph. You know, I take a photo of Darius, and of course I want like kind of a regal look, so I would like the background to be blurred out so that we just focus on his face. Right? How could I do that? I could get a nicer camera that has depth of field, or I could just trace him out and blur everything else. Yeah, so that's sort of our simplest example of an image filter that blurs. And what is a blur? In some sense, is taking the value of a pixel and replacing it with the average of that pixel and some of the pixels nearby. Yeah? And so another name for this is convolution. So here, let's say that the weighted average, the weights of the weighted average form like a little box. So in other words, like I'm just going to take the pixels within some little neighborhood of the center and just add them all up and divide by n, right? So a different way to think about that is there's a box of height 1 over n that I'm like kind of sliding along the image, multiplying the two together and then summing. Does that make sense? And the box would be our convolution filter, and the output would be the thing that we get from convolution. So here's an example of what this looks like. So here is my photograph. It's a very simple photograph of a checkerboard. And here's my filter. So what am I saying? I'm going to replace every pixel here with the weighted average of this pixel and its neighbors, where the weights, you know, are maybe the highest in the center and drop off as I go to the outside. And so what does image convolution do? Well, I kind of take the green guy, stick it on top of the gray image, multiply the two and add to get the pixel color. So for example, if I wanted the color of this pixel, this is like the extent of my PowerPoint skills, by the way. You should all be very impressed. I'm going to take that green filter, put it on top of that pixel, right, multiply the two and add, and then what I get is the output color here. And so to fill in the remaining pixels of the image, what do I have to do? So there's my color. Now I can just slide the green thing along and get all the remaining colors in the image. And then eventually what I get is the outside. Now, what detail did I just slip past you guys? Yeah.
You should start the center of the kernel in like the corner instead of.
Yeah, I kind of forgot the leftmost pixel in this row, for example. And the reason for that is, well, what's going to happen there? I'm going to put my convolution kernel, right, this green function, and it's going to hang over the side. And I don't have a color there. So what do I have to do?
Extend the image.
Yeah, I got to make one up. Yeah, and there's no like God-given way to do that. It kind of depends on your photograph, right? So a very typical thing to do might be, say, like just clamp. So in other words, like if I look beyond the edge, I should just, you know, take the coordinate and just stay on the left-hand side. You have to be a little bit careful with that because it puts undue weight on the sort of outer edges of your image. Or maybe your image wraps around itself somehow, like I'm taking an image of a brick building or something. And so you can make use of that kind of thing. This is called a boundary condition. Okay, so this is an image convolution filter. And the green guy is called a kernel. Typical properties of the kernel is that they sum up to 1, right? Because you want them to be kind of weighted averages. And they're relatively small, meaning that that little green patch typically isn't so large in a lot of image processing applications. There's both an algorithmic reason and an artistic reason for that, right? So artistically, I think if they were giant, you get like some giant blur, which might not be that exciting. Algorithmically, at least in the technique that I've outlined for you here, what's going to go wrong? Like, yeah.
I mean, you need to do one, like, you're multiplying by the number of things in the kernels. If you have 5 by 5, maybe 25 passes through the entire image.
That's exactly right. So like if I want the output color of this red pixel here, well, I've got this 3 by 3 kernel that I put on top of the input, and I have to sum and multiply. Right? So the bigger my kernel is, the more computational work I have to put into computing the output color. Now, that'll turn out not to be true. There are techniques using Fourier analysis that get around that, but at least kind of initially that seems to be the case, which is a bit of a problem. In any event, there are many different convolution kernels out there. So for example, a kernel which just is kind of big in the center and drops off, if you think about it, is just blurring out an image, right? So for example, here's Taj Mahal. If I choose, you know, some pixel right on the edge here, I'm going to draw a little neighborhood around that and average all the colors together, which is going to get some blue and some white. And so what I get out is a blurred Taj Mahal. Yeah. A different thing I might want to do is like find all these sharp edges in this photograph. What's a sharp edge? It's like somehow a pixel that's different from its neighbors. So one thing I could do is take the pixel value at the center and just subtract off its neighboring values. And if that difference is really big, then I have an edge. So here's a convolution kernel that does that. So maybe I have +4 here and -1 on the edges, or on the neighboring guys. And then what I get back is this kind of funky image, which you've probably seen in like photograph tools every once in a while, which is big anytime that a pixel is kind of an outlier, right? This is also called the Laplacian filter. If you take my graphics class, you'll see why, or my grad class rather. Yeah.
Is it supposed to look similar to like, I forget which one, but like the high pass, low pass filters that we were looking at?
Yeah. So this is a high pass filter, absolutely. In fact, you can prove that. Yeah. Right. Here's another kind of funny effect that I feel like you see a lot in the 1980s, which was called embossing, right? Where you kind of wanted to like shift your image a little bit and make it look like it pops out a bit. So one thing you could do would be like add a little bit on the bottom right, subtract a little on the bottom left, and this creates this kind of funny effect. One thing to notice is, of course, this algorithm, the way that I've described it to you is pretty slow, right? So if I have a photograph, which is n by n, and I have a convolution kernel that's m by m, then the amount of computation time that I need, well, for every pixel, right, there's n squared of them. I've got to do m squared work. That's really a problem. And so a lot of effort in electrical engineering and computer science has gone into making that faster. So for example, the fast Fourier transform is one kind of standard technique that helps you get around that. And really, this creates a lot of problems. So if you do your approximation incorrectly, you can run into a lot of trouble. So for example, remember that we want to convolve things against sync. One of many problems with sync is that its extent is infinite, meaning that your convolution kernel is really, really big, right? So that would be an example where you really do care about making the computation time faster. Another one that you often care about is convolving against a Gaussian. Do you guys remember what a Gaussian is? It's like e to the minus distance squared. So this is a kernel that's big right at the center and drops off isotropically as I move away from the inside. The Gaussian kernel has a really interesting property, which unfortunately in the 10 minutes we have remaining, we're not going to be able to prove, which is that convolving an image against a Gaussian in x and y, in other words, replacing a pixel with its weighted averages, where the weights are dropping off like e to the minus distance squared, is the same as first blurring vertically and then blurring horizontally. And that's because a Gaussian is known as a separable filter. This is actually not terribly difficult to see. Like if you take e to the minus, distance from x to y squared, and then expand the square, it's like the product of those two things. This is essentially all that's going on. And so what does that mean? That means that I can take my image and do two blurs, but each of those blurs only operates on the columns of the image, or the rows of the image. So I've shaved off one of the factors of m here. Do you see that? Because in every pass, now I only have to move vertically or horizontally, and when I put those two blurs together, I get exactly the same thing. What does that mean? That means we actually only have to be good at convolving against 1D things. So let's say that the only thing I cared about was Gaussian blur. I just really want that nice photograph of Darius with the background blurred out, right? So I've reduced this to a one-dimensional problem, right? I can do a bunch of horizontal filters and then a bunch of vertical filters. Does anybody have any ideas how I can make this even faster? If you've taken a statistics class, you've probably seen Gaussians, otherwise known as bell curves or normal distributions all over the place. Does anybody remember a famous theorem involving the normal distribution? The central limit theorem. That's exactly right. So here's the central limit theorem stated in graphics terms. It says if I take an image and I blur it with any kernel enough times, eventually the resulting thing will look like an image convolved against a Gaussian kernel. This is exactly the central limit theorem. So the central limit theorem, the way that it's usually stated in statistics is like I take a bunch of samples from some probability distribution, I average them all together, and eventually they look like they're distributed by a Gaussian. And it turns out exactly the same machinery appears here. So what is the end result? Well, what it means is like Gaussian convolution is kind of hard, right? Gaussians, e to the minus x squared has infinite extent. It's like a hard function to work with. It requires computing exponentials. But convolving against other things is quite easy. So in particular, convolving against a box is a very straightforward operation, right? Because a box is just a weighted average, right? So I just like take the 5 pixels nearby, I add them up, and I divide by 5. Yeah? So what do? I take the row of my image, I convolve against the box. If I convolve against the same row against the box a second time, you can see that ends up being equivalent to convolving against a triangle. If I convolve against the box a third time, it ends up being against a parabola kind of looking thing. And a fourth time, fifth time, and so on. So what did we just do? We said, okay, well, Gaussian convolution is kind of annoying. So instead, we're just going to convolve against the box 1, 2, 3, 4, 5 times, and it's really, really close to that output anyway. And essentially, what we're using is actually a statistical theorem. This is central limit theorem. So here's our one last little observation, then I'll let go of this for the day. How do I convolve against the box? So far, our algorithm is n squared m time. Right? Remember what that means. That means in order to convolve against a row, I have to do m work, where m is the width of my filter. Right? The reason is I'm doing that weighted average along the row. I claim you can do this in order 1 time per pixel when you just convolve against the box. And here's our sneaky way of doing that. So what I'm going to do is I'm going to compute for the leftmost pixel his box weighted average, right? So that's like some over here. Now, what do I do when I want the second from the leftmost pixel's box weighted average? Well, notice that those 2 rows of pixels basically overlap, right? There's 1 pixel on the left and 1 pixel on the right that are different. So when I want to take the weighted average, which is just like the sum, you see that? It's like the sum divided by 3 here. Well, if I wanted that for the next one over, all I really have to do is take this guy's weighted average, subtract 1/3 of this pixel color, and add 1/3 of that pixel color, and now I have the next guy's weighted average. That is an order 1 operation. Right? It's 1 subtract and 1 add. Yeah? So this is now order 1 time per pixel to convolve against a box. Only works for a box. But if I do it a bunch of times, that box becomes Gaussian. And so this is a really, really fast way to convolve against this nice Gaussian blur. Yeah?
Doesn't that mean that you now need to compute them in sequence though, so you can't do them in... Oh, well, you can do
But I can parallelize over all the rows of my image. Yeah. This is actually quite fast. Yeah. Of course, this is just approximate, But the nice thing is that it just, the computation time here is the size of your image multiplied by the number of times that you apply a box filter, which is not actually so bad. Yeah. Of course, there are many different techniques for blurring stuff out. Another one is known as the Gaussian Pyramid, which is kind of like how we computed the bitmaps. So in this case, what you do is you kind of iteratively shrink your image by half, and actually by kind of a similar piece of theory, you can show that that filter also looks an awful lot like a Gaussian distribution. One thing you'll notice if you go into image processing, which is a fun universe to be in, by the way, the coding is way easier than most of what we've done in this class because it's all 2D, is that the details really matter, and subtle things can go wrong that are like basically examples of stuff we've seen in this class and basically only talked about in theory. So here's a nice example. This is my colleague Andrew's dog, because he did the example and I reused it shamefully. And what I've done is I've rotated it 30 degrees 12 times. So I took his dog, I rotated it 30 degrees, then I took that photograph and I rotated it 30 degrees more, and I did that a bunch of times until the dog went in a complete loop. I was lazy about boundary conditions, so we're just going to ignore the outside. Okay. Now, instead of doing that, I'm going to rotate my dog, Andrew's dog, 5 degrees 72 times. Do you see what happened? Let's toggle between these images a little bit. Looks crispy. Yeah, crispy is the theme of the day. In fact, let's make it even worse. So let's rotate 1 degree 360 times. And here's the result. Anybody have any idea what went wrong? Yeah.
You're doing more and more like interpolation.
That's absolutely right.
So the more times you rotate, you're going to have more and more interpolation. You have less and less real values.
That's exactly right. So this is a great example where every time I rotated this image, I had to make a little bit of an approximation, right? I had to interpolate. In particular, in this case, I wanted to do my interpolation nicely, so I used some nice approximation to that sinc function known as Lanczos 3. And Lanczos 3 has an unfortunate property, which is it dips just a tiny bit below 0, right, as the sinc function should. But what does it end up doing? Well, this is only an approximation, and that little bit below 0 ends up kind of building up quite a bit and pushing this image toward its extremes, and what comes out is something useless. The takeaway here is twofold. One is that everything here is approximate. The other is when you implement these kinds of tools, what you should not do, and what a lot of the old versions of the software did do, was like, okay, first I'm going to blur out my image, and then I'm going to increase the contrast, but then I look at it and I say, well, I want to blur it a little more, so I do that, and then maybe I want to change the color, so then I do that. What we used to do is just edit the pixel values and then save the result. And what ends up happening is the error in that saved image is a composition of all the errors that you put together, right? And so the more modern software will actually keep the original image plus the tree of operations that you've applied so that you can undo them and apply them more carefully when they're composed together. Okay. And there are a lot of different filters that kind of are useful to know. Another good one is Unsharp Mask for increasing the contrast. So here, maybe I blur out my image, and then I amplify the difference between the blurred out image and the original sharp one. So this has the effect, for example, here's a photograph of a spiral. You know, when I blur it out, this edge gets lost, and so now I'm kind of pushing the pixels away from that blurred out edge value. You see this a lot in poorly filtered images. The way you can spot it is something called a halo artifact, right? Because right around the edge here, the blurred out image doesn't know there's an edge, but the contrast enhanced one does. And so, for example, right on the skyline here, you get like kind of a weird false artifact that wasn't there. Convolution is basically an example of something we call a linear image filter, meaning that it really is a linear function of the input images. And the problem with linear filtering is exactly that it doesn't know anything about your image content, right? It's like totally brain dead. Like the convolution filter just walks along the image and doesn't actually look and say like, oh wait, there's an edge here, I should do something different. So the more advanced stuff, if you take Fredo's course, is all about nonlinear image filtering. Right? So let's say that I want to blur out a photograph, but I want to preserve its sharp edges. Then there's a nice technique known as bilateral filtering that takes the Gaussian kernel, but then says, well, wait a second, if I have two pixels that are very far apart in intensity, I shouldn't put them together in my weighted average. So maybe I modify the weights in my weighted average to account for differences in pixel color. That's a great idea in concept, but now all these cool algorithms we talked about for convolution are no longer relevant. You have to go back to the drawing board and come up with much more advanced techniques. but the results can be pretty impressive. So here, right, if I Gaussian blur a photograph, obviously I just get a blurry mess. If I bilaterally filter a photograph, then at least roughly some of the sharp detail is preserved at one scale, but the sort of noise locally gets blurred out here. And there are all kinds of cool nonlinear image filters out there. That's one. Another good one is median filter, where I take every pixel in an image and I replace it with the median of the colors of the pixels nearby. Medians are really nice because they only depend on one data point. Right? So if you're taking the stats class, you might remember that medians are sort of outlier resistant. Right? Like averages, if I take the average of 10 numbers and one of them is a giant outlier, that's a big problem because it throws off the whole average. But the median isn't affected by that at all. So this happens a lot in photography because photography often has what is known as shot noise. So here's the thing, when you take a photograph of a darkly lit scene, there's an issue, which is every once in a while your sensor may get just like 0 photons going into it, right? And then you'll get just a noisy pixel, or maybe you get an extra photon and that actually makes a serious difference. So in the sort of shot noise model, when a pixel looks good, it looks perfectly fine, but every once in a while you have a useless pixel. Then things like the median filter make a lot of sense. And sort of a nice notion of blur. If you want a good challenge problem to think about, the question is, how would you do a median filter quickly? So in other words, I want to take a photograph, maybe just black and white is good enough, and for every pixel I want to replace it with the median of the colors of the pixel in some neighborhood of that center guy. So this box filter trick doesn't quite work anymore, but maybe you can use a similar intuition to build a new algorithm. So anyway, with that, this is our whirlwind introduction to the kinds of things people think about in image processing. These are interesting problems, completely different, but still part of the graphics world and our big bag of graphics stuff at the end of the semester. Next week, we'll talk about GPUs, and then we're pretty much done. So anyway, with that, have a lovely weekend. If you want your exams, maybe we'll bring them up here would be the best way to do it. I'll hand them out personally. That's it.